Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam. So, we were in the organic, and yesterday we have completed the haloalkane part. So, today we will be starting with the haloarine. Okay, so this is the JEE syllabus, so it's mostly include this haloarine and its preparation and reactions. So, I will not be moving to this environmental effects of chloroform, iodoform, pherones, and DDT as it is not much important from the JEE point of view because the questions are not much, no, not much asked from here. Or you can say the percentage is much more lower, so it should not valuable to consider it as in the crash course. So let us start this discussion. So these are the topics that will be covered today. So first we will move to the preparation of haloarine. Then we will move to a very popular reaction, that is the Sandemer reaction. Then we'll move to the chemical property or the chemical reactivity of the haloarine. So we will see how it is doing the nucleophilic and how it is doing the electrophilic. So we will see various aspects of it. At last, we will be covering it the examples of electrophilic aromatic substitution. And this is the weightage. So we have seen this earlier also. So one question is asked on average from this organic compound containing halogens, which is of 4 marks. So this is the very basic method that is used in the preparation of haloarine. So we can do the chlorination, we can do the bromination, and we can do the iodinization. Okay, but we cannot do the fluorination because the CF bond is much more stronger. Means the FF bond is much more stronger, and it is not a good Lewis acid also at the same time. So we will see how this reaction goes out. So we are doing here a halogenation using a electrophilic aromatic substitution of this benzene. So we are taking a salt of iron, or you can say LCl3. So both act as a Lewis acid or Lewis. So these are acting as a Lewis acid here. Now first of all, this AlCl3 or this FeCl3 react with Cl2 to form this AlCl3 react with Cl2 to form AlCl4 plus, sorry, AlCl4 minus, and this Cl plus. Now this Cl plus is the electrophile here. So this Cl plus attacks this benzene ring, and we get this benzene here or monosubstituted chlorobenzene here. Plus HCl is released. Similarly, if we take Br3 in plus of AlCl3, then we will give this Br2 plus Br2 will give this bromobenzene and HBr, hydrogen bromide. Now the thing that is to be noticed here, that for iodine the case is different. Why? Because this Hi is irreversible, which it reacts back with this whole compound and give the reaction back. So this reaction is irreversible. For that reason, we use HiO3. HiO3. So what does it do? It reacts with Hi, okay, and give us 3H2O and 3I2. So this is released as gas. Now further, this Hi does not react in the backward direction. So we get the product in major amount. So this should be kept in mind that for chlorine and bromine, we do not need any such kind of reagent. But for this iodine thing, we need this HiO3. Okay, so this is done in the presence of HiO3, and this HiO3 react with Hi to give H2O plus iodine gas. Now the thing that is to be noted here is that this reaction is not possible for fluorine. So you cannot use here F2. Okay, in the presence of anhydrous AlF3. So this type of reaction is not plausible. Okay, so this cannot be considered. So for that reason we have the Sandemer reaction. So Sandemer reaction is not only useful for preparation of haloarine and haloalkene, it is very valuable in any means in any substitution of this benzene ring. Means a numerous amount of product can be formed using this Sandemer reaction. So this was all about the preparation of haloarine. Now we will move to this Sandemer reaction. Okay. So this is the Sandemer reaction that we have. So what is the initial substrate? That is the aniline. So if you want to build this aniline, you can do it in various ways if you want. So we know that we can do the nitration of benzene. So we have seen this nitration of benzene in the hydrocarbon also. So first we will use a mixture of HNO3, okay, and H2SO4 to nitrate this. Now this will be nitrated and NO2 will be added. Now we'll simply reduce this using any reducing agent to get our required aniline. So you may be asked in the examination from the benzene part also, not directly from this here. So you can be given the reagents in this order, that this is the first, this is the second, and this is the third, and you have to tell your final product. Now this diazotization reaction, so it is also called as diazotization reaction because this diazo, this N2 plus is added here and X minus. So what we do, we take at this temperature is very important. Okay, so this temperature is important for the conservation of this product very well. So we take NaNO2 plus HX and this gives us N2 plus and Cl minus. So generally we take excess chlorine and bromine only. Okay, so we do not take the iodine and say fluorine part. We take the chlorine and bromine only. Then we can easily nucleophilic using the nucleophilic substitution. We can replace this Cl and Br that is formed here, that N2 plus and X minus it can be here Cl and Br. So if we react it with CuX in the presence of 600 to 100 degrees Celsius, and X can be chlorine and bromine, then we will get this chloro and bromobenzene. So this is for the chloro and bromobenzene. We use the copper salt of the same halide, that is chloro and bromine, chlorine and bromine. Now for the introduction of this I, okay, so for introduction of this I, we use this Ki, potassium iodide, and this is replaced by this whole of this N2 plus X minus, because this N2 plus is a good leaving group. So how does it leave? So if you see it is like this, okay, and now this whole thing is attached to the phenyl ring. Now what happens is that this is a positive sign here on this nitrogen, okay, and there is a X minus. So this positive sign is on this nitrogen because it is forming 4 bonds, 1 bond extra. Now what happens is that, sorry, okay, so this bond, it goes on this nitrogen, so the positive charge is neutralized, and this pH, a phenyl type of cation is formed. And now this temperature is important here because it can be stable only at this temperature. So this is a kind of concentrated mechanism, so it does not like it happens like this. The phenyl cation will be formed and then the group will leave and then the third group will attack, so it does not happen in that way. So a concentrated mechanism means in one step the means the attacking nucleophile comes and this N2 plus leaves and we get the final product. Now for for iodine we use this Ki. The introduction of CN group is very important because further we can just hydrolyze it to get our carboxylic acid, or we can say we can use any methylating agent and increase the length of the chain also to get further derivatives of this benzene. Now the common part in all of this reaction is that N2 is released, and N2 is a very good leaving group because N2 is formed with high anisotropy, high means large amount of heat is released during this reaction. Now this H2SO4 also can be got in the same way. Now the main good for this Sandemir reaction is the introduction of the fluorine part here. Here you can see, so if we react it with HBF4, then HCl is released, N2 plus and BF4 minus is formed. Then further on heating this one, so if we have to heat this one, then we will get this following product, which includes a fluorobenzene as well. So this is the main use of the Sandemir reaction. So it can be used to form any substituted benzene from normal benzene. So we can take the normal benzene, just nitrate it, then reduce it, and then further you can do the diazotization, that is this part, and we can use the various nucleophiles CuX, Ki, CuC, and H2SO4 and HBF4 and other nucleophiles also, and we can get our required derivative of this benzene ring, or you can say substituted benzene ring. So this is all about this Sandemir reaction. So what makes this Sandemir reaction very feasible? The release of this N2 group or the nitrogen gas, which is released, or you can say it is a very good leaving group. Now if we move to the reactivity part of this haloarine, so you can consider this as the plus M effect that is occurring here. So I will give you a trick in the later on slides to how to decide that something will give plus M or something will give minus M. So there is a simple trick for it. So for now, consider that this halogen is giving the plus M effect. So it has three lone pairs, 1, 2 and 3. Okay, so these are three lone pairs. Now one lone pair will just go into the, say, benzene ring and activate this ring. So the point that I want to make here is that, so if something is donating electron in the benzene ring, it is activating that benzene ring because we are getting a higher density of electron around the benzene. And now the electrophile that is to come, means the electron loving group that is to come, will be attracted more due to this presence of, say, halogen group or any lone pair containing group. So we will generalize this on the later slide, that which will give its lone pair and which will not give. But for now, consider that, okay, halogen is giving its lone pair and it is activating this group, this benzene ring. Now, due to this, say, resonance part, we get a double bond, partial double bond character between this C and X. So you can see that in out of this four resonance structure, sorry, 1, 2, 3, 4, 5 resonance structure, three of them have a C double bond X. So this one is having a C double bond X. This is also having a C double bond X. Now, due to this resonance structure, it has a partial double bond character between C and X. And this negative charge is not localized, or you can say this electron pair is delocalized all over this benzene ring. So it goes from ortho, then goes to para, then again goes to the alternating ortho, and goes back to the halogen as a lone pair. So this is a kind of ortho para directing group, and this is the resonance hybrid that we have. The electron is like a cloud that is delocalized over all the carbons, plus it is delocalized between carbon and halogen also. So this is all about the reactivity of halogen. Now the same thing written here, activate ring to resonance, or you can say plus M effect or mesomeric effect. Now one exception is there, that the chlorine that is present here, if chlorine is present in place of X, so if X is chlorine, then it shows a exceptional behavior due to greater inductive effect. So what is that exceptional behavior? So exceptional behavior is that it deactivates the ring. Deactivates the ring. Okay, now let me make this point clear. So this benzene ring is still orthopara acting if chlorine is present here. But the difference between the orthopara action of this other halogens, that is fluorine, bromine and iodine, and between chlorine is that all of the halogens activates this ring, but chlorine deactivates the ring. So what is the reason? The reason is due to the greater inductive effect, means it shows the M effect and it shows the I effect. So all the halogens shows this all, because say you know very well that halogens are electronegative in nature. So as they are donating electrons through the resonance, they are also attracting electrons due to their greater electronegativity than carbon. So there is a kind of inductive effect, but due to, you can say, means if you consider fluorine for the case, which is more electronegative than chlorine, but instead of say deactivating this group, although having the plus I effect more, sorry, minus I effect more, it activates the group. Why? Because if you consider the periodic table, chlorine, this is carbon, this is fluorine in some place, means you can see that fluorine and carbon are on the same period. So due to the same period, their outer shell is on the same energy level. You know very well that, okay, across the period the shell remains same. Now due to the lesser energy difference between the orbitals of this carbon and fluorine, the electron giving tendency of this fluorine, or you can say resonating tendency of this fluorine lone pair, is much more greater than this chlorine. So although this fluorine having a greater electronegativity, it shows a greater mesomeric effect due to lesser difference in energy between the orbitals of the carbon and fluorine, because the carbon is taking the electrons, so it is, and fluorine is giving the electrons, and both of this valence shell are almost the same energy. So this resonance effect takes place in a more optimizing way as compared to the chlorine. So this chlorine has a greater electronegativity also than carbon in the first place. And the second place, it is not as it is not as good in giving electron to the carbon because of the greater energy gap between the lone pair of the chlorine and the, you can say, empty orbitals of the carbon. So they deactivate the benzene ring. So this point should be kept in mind always. So if you are told that okay, give which of this reacts faster, means which of this goes electrophilic aromatic substitution faster, then chlorine will be at the backwards because of this deactivating nature. Now nucleophilic substitution is difficult for this halogen. So this was all about electrophilic aromatic substitution because electron are being given to this benzene ring and they are now attracting the electrophile. So if you consider the nucleophilic substitution, so it is difficult, it is not impossible, but it is done at high temperature and pressure. Means a rigorous condition is made and then only the substitution can take place. So we will see why is it so. So one of the reason that you can say is the double bond character. So it is also mentioned in the next slide also. So because this resonance uh, structures are not there, so I am making just a point, first point here, that due to this partial double bond character, it is difficult to substitute this X, or you can say remove this X. Now there are many more reasons. The first reason I have told you, that partial double bond character due to resonance. Now second is the instability of this phenyl cation. So if you are substituting a phenyl, okay, so suppose this is X. So first this X will leave and we will get a kind of this, okay. But this phenyl cation, okay, this phenyl cation is not stable, okay, because it lacks aromaticity also, because it's difficult for this to be aromatic because conjugation is lost here. Now next, repulsion from electron cloud on both sides of benzene ring. Okay, if you have seen the previous lecture, you must have seen that the benzene ring is surrounded by two electron clouds like this. So if you see this diagram here, I'm drawing it here. Okay, so we have this, say, a kind of benzene ring. So it is surrounded by an electron cloud from the up and down side both. Okay, so there is an electron cloud in the downside and there is an electron cloud on the upside. Now if any nucleophile has to come, because this, why is it so? Because of the delocalization of the lone pair all over the carbon. So it is surrounded by a electron cloud both on the top and bottom. Now for the upcoming nucleophile, it becomes very difficult to approach this, because nucleophile, you know that it is positive loving, and you can say it is having a partial negative charge or a full negative charge. So if there is electron cloud, electrons are having nature of a negative charge, so they will repel that nucleophile or the incoming nucleophile, and it will become difficult to do the nucleophilic substitution. Now due to these three reasons that I have given, okay, due to these three reasons, it is difficult for a halogen group to do the nucleophilic substitution. But still, we can do this under high temperature and high pressure. So what we do is that we take NaOH, okay, at 623 Kelvin, that is a very high temperature, and 300 atmospheric pressure. So let me remind you that our atmospheric pressure is 1 atm. So suppose this pressure is increased up to 300 times. So that much high pressure is required, plus the acidic condition. Then and then only we will give this nucleophilic product, that is Cl will be substituted by OH. Now, one of the reason that is inhabiting this nucleophilic substitution is this electron cloud. So if by any way or any means, if we reduce this electron density by introducing an electron withdrawing group on this benzene ring, then we can substitute this benzene ring in a much easier way, we can say, in not a general way, but in a easier way, we can say, if we allow some electron withdrawing group to attach to this benzene ring. So I have given some examples. So first, this is the example that we are introducing one NO2 group, okay. Now this NO2 group will say, this is the meta position for this, okay, or you can say all our benzene ring is deactivated due to this NO2. Sorry, this is the ortho, this is the para, this is the ortho, meta, and para. Yeah. Now, if you do the electrophilic aromatic substitution, sorry, nucleophilic substitution, it will be much easier. Why? Because we can see here that we have not done anything on the pressure. Also, at the same time, we have reduced this pressure from 623 to 443. So 443 is written here. So we are reducing the temperature also, although we are getting the nucleophilic product. Now in the second case, we introduce rather 2NO2. Now furthermore, this temperature is reduced very much. So from 443, we go to 368. So we require even a less temperature. At last, it we introduce 3 nitro group here at both ortho and para. Then we can see that by just warm water. So we are using just warm water, warm plus H2 and nothing else. We are easily getting this 2,4,3 trinitrophenol, and it is commonly known as picric acid. PICRIC. Sorry. Yeah. So if we just introduce this warm water, then we can easily substitute this chlorine by OH. So you can see very clearly that this very reason is being removed by introducing as many as nitro group we get on this benzene. So first, if you introduce the first nitro group, the temperature goes from 623 to 443, the pressure constant is removed. On further introduction of 2 nitro group, we get from 440 to 368, and on introduction of 3 nitro group, we just have to put the warm water and we get our nucleophilic product very easily. And this is called as picric acid. So this is a reaction important for you. So you can be asked in the exam directly from here. Okay. So this was all about the nucleophilic substitution. Now we will move to electrophilic aromatic substitution. So I've not put up the picture of the electrophilic aromatic substitution mechanism because you know it very well how it happens. For those who don't know, I'm just making a short we can say a note here. Now what happens is that if an electrophile comes, that is E plus, it goes here. Okay, it takes this pi bond, takes the electrophile, and we get one electrophile plus this hydrogen, and a positive charge is built here, which is delocalized all over the ring. So this is the intermediate that we have. So if we draw the resonance hybrid, it looks like this. So it is not only there on this part only, so it is all over the carbon. So here is the E, here is the H. Okay. So this is the hydrogenous hybrid that we have during electrophilic aromatic substitution. I have not shown the delocalization again. We have studied in the previous class also. Now, how will decide that something is giving a minus M or a plus M? So there is a simple trick to it. Okay, so if say this is the group that is attached to the benzene. Okay, so this is the group that is attached to benzene directly. Okay, so this is position A, it is attached to B, and we have a double bond just consecutive to it, or a triple bond just consecutive to it. Now this both of this group will show the minus M effect. How? Because this double bond will move here and this lone pair will go on bromine. Similarly, this double bond will move here and this bond pair will move on bromine. So this both will show minus M effect. And what kind of product it will form? It will form meta product, and it will be deactivating. So generally, because we have seen a case where it is ortho para directing, and but still it is deactivating. So we are not just saying that all of the reaction will do this, but if it is meta directing, then almost all of them will be deactivating one. And the product that will be formed. That means the electrophile that will come, it will be going on meta position here, 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 or here. Now let us move to another, that is plus M effect. So this plus M effect is generally shown by those which have a lone pair. So this is the halogen. So we are considering halogen competing compound. So we'll consider that only. So if we have a plus M effect, then we will get ortho para effect. So first of all, this is clear for all of you. So it will give ortho para effect, and it can be it is activating. Okay, just this chlorine is the exception here because of the chlorine is an exception, because although it is say orthopara directing, it is deactivating the group due to higher electronegativity and thus minus I effect, greater minus I effect. Now since this has a lone pair, this lone pair goes throughout the benzene ring, and we see a plus M effect, and the product that we are getting is a orthopara one. Okay, so this is all about the electrophilic aromatic substitution, and we will be considering this one because we are dealing with halogen. So we will see also para direction with plus M effect. Okay, so let us see some examples. So this is the examples we have. So first of all, we have this FeCl3 and Cl2. So we are taking a chlorobenzene and doing the electrophilic aromatic substitution by nitration, sulfonation, Friedel-Crafts alkylation, and halogenation. So if we react this FeCl3 and Cl2, we will get FeCl4 plus Fe plus and Cl. Okay, Fe minus, Fe plus. So we will get a Cl plus electrophile, and this Cl plus will be attacked by the chlorine, and you will get this orthopara group. Now majorly this para will be formed because of the steric regions, because this chlorine will repel each other. That is why we will get the para in the major amount. So all of these cases, para will be in the major amount. For nitration, we use the mixture, that is H2SO4 plus HNO3, and we get this type of okay, so 3 to 5. Yeah, so this is the electrophile that we have. Now the attacking nucleophile comes here, and one of the lone pair goes here, and we get NO minus and plus. Okay, so this is the nitration process we have. Then next we have the sulfonation, so we just use the H2SO4, and we get the sulfonation at the ortho and para, and still para is in the major form. Then we have the Friedel-Crafts alkylation. So what do we use? We use AlCl3 plus CH3Cl. We do have this acylation also. So in this case, AlCl3 that is an acylation case. So this is the electrophile that we have. So this is the electrophile we have in the case of acylation. And for the alkylation, we have this CH3 plus, because this Cl goes with the AlCl4 3 and forms AlCl4 minus and CH3 plus. So these are all the examples of electrophilic aromatic substitution. So all these are same as this benzene. Only the difference is that we have this para as the major one. Why? Because we are having a less kind of steric hindrance in this para product. So this was all about the haloarine. So we have not covered this, say, chloroform and all parts. So it is not important, as said earlier also. Now we'll move to some questions and see what are the questions that come in the exams. So I've picked some exam questions that are almost framed like your JEE exam. So the first is that the total number of alkene possible by debromination of 3-bromo cyclopentane hexane. So what we are taking? We are doing a dehydrobromination of 3 bromo cyclopentane hexane. Okay, so this is the 6 carbon that we have, and the cyclopentyl is present on the third position. So 1 2 3 4 5 6, and also the bromine is present here only. So I'm not drawing the hydrogens here. Now what do? We do the dehydrobromination. So what is dehydrobromination? So basically we are removing minus HBr. Okay, so let me do it here. So we take this, say 3 on this, 3 on this. We take the bromine, hydrogen. Also we have a hydrogen here also. I'm not mentioning the remaining ones. Now, three kind of bromination can happen. So three alkene are possible. The first one is that we remove this hydrogen. So what we will get is that, so I'm drawing the bond line structure. The first one is this. The second one that is possible, so it is 3 bromo, 3 bromo, 3 cyclopentyl hexane. Okay, yeah. And the second one is 1 2 3 4 5 6. 1 2 3 4 5 6. Yeah. 3 4 5 and 6. So one more carbon is here. Sorry. Yep. 1 2 3 4 5 6. Yeah. Here we have this. Yeah. So this is the product. So second product will be this one. And the third product that is possible is this. 1 2 3 4 5 and 6. So it will be on this side. So first is this one, second is this one, and third is this one. So these are the all three alkene products that are possible from the reactions. So what is this reaction? So if you have not seen the reaction, so it is basically we are using alcoholic KH, and this OH minus does the elimination, remove this bromide group by taking this H here. So it takes this H here. Suppose this OH minus comes, it takes this H here, and we get a alkene. So 3 are possible. So 3 is the correct answer. Now next, let us do this reaction. So it says that we are taking this group, okay, and we are reacting it with HCl. So what is the final major product that we get? So if we write this structure here, so we can write it as this, a benzene. Then you have two carbons that are sp2 hybridized. Yeah. So this is the one. Now what we are reacting it with? So we are taking an HCl. Now, what are the cases that are possible? So alkene takes this H plus. So we are adding this hydrogen H plus. So this H plus will be taken by alkene. So what are the alkenes that are present here? So 1, 2, 3, 4 alkenes are present here. So this one, this one, this one, and this one. So this hydrogen can go to any of these three. Now let us rule out the possibilities that are not worth it. So these three are not worth it at all. Why? Because if we do so, we are just disturbing the aromatic nature of this whole benzene ring. So first of all these are removed by one shot, and we get this one. So we will do the H plus addition at this carbon. Now two cases arise, so we can add this here and we can add this here H plus. So we know very well that if we add here, then we will get a positive sign on secondary carbocation. Okay, so we'll get a secondary carbocation, and we know very well the secondary carbocation is stable as compared to the other one, which will be primary one. So this hydrogen will be added on this H. Now before you attack the Cl minus here, we have a different kind of rearrangement. Why? Because this positive sign is much more stable here. Why? Because it is stabilized by this whole benzene ring. So what will happen is this, there is a kind of 1 to hydride shift. So this hydride will go here and we will get a benzyl cation, and which is very much stable due to this benzene stabilization, or you can say resonance stabilization, means it goes whole through this group. So we get this kind of resonance hybrid. The positive charge is distributed all over this. So the Cl minus will finally attack here, and we will get this product as the major one. So this is the correct answer that we are having. So this is a rearrangement kind of reaction. So you must be considering this part also, because we will go through this, say, carbocation formation, and then since the carbocation is more stable, the benzyl carbocation is more stable than any other, so we'll get this product. Now to the question third. So question third, we have this FeBr2. So we have to do this bromination. So do not get confused that we are using this FeBr3 and Br2 for bromination, but here we are using a different one, so it doesn't matter at all. So if we use this FeBr2, it will give the same product. Now cases arise, so many more cases arise here. So if you see, four cases are possible for this structure to be brominated. First one here, second here, third here, and fourth here. So these are the four cases that are possible for bromination, or you can say electrophilic aromatic substitution by bromine. Now, which one will be happening? So if you consider this group here, so this is a kind of deactivating group. You can compare it with this. Okay, so you will thought like this, yeah. So it is similar to this. Now, what will happen is that it will deactivate this ring slowly. It will take this this bond pair here, and it will deactivate this ring. Now, this ring is deactivated due to the presence of the acyl group. Yep. So this is not suitable for electrophilic aromatic substitution as compared to this ring, which is getting a lone pair. Yeah, you are getting a lone pair here, that is roaming throughout this ring. So this ring is activated by this nitrogen, whereas this ring is deactivated. So this is not be showing electrophilic aromatic substitution because of this group, which is showing a minus M effect. Or you can say it is deactivating the ring. So the electrophilic aromatic substitution will take place as this ring. Now the question arises where? Now since it is a ortho para group, so we have ortho position occupied beforehand. So we are remained with this para position, and also we know that is a the reaction will take place here because it is sterically less hindered. So this is the meta position. Here it cannot be done. So we will take the this position at the final one. So this will be the final product. Okay. This is your answer, B1. Now let us move to next question. Question number 4. So toluene react with excess of Cl2 in the presence of sunlight to give a product which one on hydrolysis followed by reaction with NaOH gives. Okay, so the reaction is that the first is we do is the chlorination, but it is written very clearly that we are doing it in the presence of sunlight. Okay, so one point I missed here, that during the chlorination of this benzene ring we do it in dark. Okay, so we do that thing in dark, otherwise it is not so it is done in the dark, some reasons. So for light we are taking this Cl2 because we know very well that this in the presence of sunlight radicalization takes place, and for the chlorination of this alkyl group, simple alkyl group, there is the mechanism that is followed is the radical mechanism. So of course there will be a radical group, sorry, there will be alkyl group that will be attached to it. Now it is said that on further hydrolysis of this group, so suppose this chlorine attached here, or you can have it anywhere, it gives the following product. Now it is written very clearly that okay, it is not done on, it is not having more than one carbon. So this can be the case, this can be the case. This is not possible because it is done in the dark. So it will be the case when we do take this FeCl3 and Cl2 in the presence of dark, then only here Cl will form, and this will be further on hydrolysis and reaction with NaOH will give the final product as this one. But since we are doing it in light, that is, it will be kind of alkyl group and single alkyl group. Why? We can say one carbon alkyl group. Why? Because we are getting the product that is having one carbon only. So it is like this CH2Cl, and this will be hydrolyzed this plus NaOH, and we will get this final product. So this is the answer of this question. Now next, what we are doing, we are taking a substrate that is having Br, Me and all of this group, and we are taking PHS minus and Na plus, and we have to tell what is the final product here. Now what are the possibilities that can have? So we are having a nucleophile, it can attack anywhere. So if you consider here, the best living group that will be considered will be bromine, and this NO2 and this F can never be removed at all because these are present on the benzene, and we have seen it earlier that nucleophilic substitution is very difficult for to be possible. It is only possible in case we are having a electron withdrawing group, then also we need a high temperature. In case of 3 nitro group we do not need a high temperature, but since there is a 1 nitro group we need a high temperature, and there is no mentioned temperature here. So simply we will take that living group only which is present outside the ring, or that is not connected directly to the ring. Now for that we have two cases. So we can have methyl, we can have bromine. Now due to the large size of bromine, this negative charge will be much stabilized on bromine as compared to methyl, that is having the carbon negative charge which is less stabilized. So we know this, that bromine is a good living group. So it will attack here. Okay. Now the question comes here that what kind of attack it will be. So we are having this nucleophilic substitution. So it can be SN1, yeah, and it can be SN2. So two cases can arise here. So it can be SN1 or it can be SN2. Now the question can be answered like this, that I've showed you a chart earlier also, that we have to see whether the upcoming nucleophile, so it is a secondary carbocation, we know well, very well, and since we know the secondary carbocation can go both sides, so it can go this SN1 also, it can go this SN2 also. Now most of you will think that okay, this is a phenyl carbocation that is present here, so it will be stabilized by this ring, but you can see that we have a deactivating group here, so it will be not stabilized by this ring. Very good. Okay, so we cannot decide directly that okay, since this is a phenyl carbocation, so it will directly undergo this SN1 reaction. So it is still a question. Okay, so what we will do is that we will consider another aspect for it. Okay, so this case aspect is that whether we are having a strong nucleophile or not. So this S minus is not a strong nucleophile. Sorry, is this S minus is a strong nucleophile because it is a strong base at the same time. So we know very well that ones which is strong nucleophile is also a strong base. Because of the large size of the sulfur atom, it can easily donate its electron. Okay, so this can donate its electron, so it is a good nucleophile. So since it is a good nucleophile, and we know that if it is a good nucleophile and the rate of reaction in case of SN2 depends upon the nature of nucleophile also, so this will go through a SN1 SN2 reaction. So we will see a inversion here. So if we will take the inversion case, so it will be inverted. So since this Br is present on the upside, so as there is a steric hindrance, it will attack from the opposite side, that is downside, and we will get this kind of inverted product. It is on the dash, so SPH is on the dash one. So this is the final product that we have here. So if you consider other products that are given, so this all are directly not included, or you can say excluded, because SPH cannot be removing this fluorine at any cost because it is not a deactivated ring, or you can say there is no higher temperature. So easily we will consider this too, and then on the basis of this strength of the nucleophile we will consider that okay, it will go through SN2, that is this one. So this is the correct answer that we are having here. Now all the 5 questions that I will solve is solved. Now I will show you the questions one by one. You will solve it by yourself. I will give you some hint if it is very difficult. So let us do this. So this is the 6th question that we are having. So we are treating this X with sodium hydroxide followed by the addition of silver nitrate gives white precipitate at room temperature. Which of this soluble in NH4OH? These are the options. This is the first question. Second question we have here, we are using Mg ether in the presence of D2O. So it will be the required product. So this is a very good question. So it is basically from Wurtz fatigue and Wurtz reaction. So I have told you the difference between all of these three. You can solve this question by yourself. Now the next one is the reaction of toluene with Cl2 in presence of this FeCl3, that is doing chlorination of this electrophilic aromatic substitution, gives X, and in the presence of light gives Y. Okay, so we have two cases. So we know very well that in presence of light we have the radical mechanism, in the presence of FeCl3 we have this electrophilic aromatic substitution. So we know the product very well here. This is the 9th question. A dihaloalkane having formula thus, so giving the molecular formula. On hydrolysis give a product that can be reduced by toluene's reagent. So this is the toluene reagent question. So for those who don't know, so toluene's reagent basically happens for that carbon which is having a aldehyde group. Okay, so this is the basic idea behind it. So if you know what is toluene's reagent, you can solve this question. Okay, so this is higher level one. So the compound X is, so you have to predict which can be the compound. So first of all you get a reference of this toluene reagent. So if you don't know, you can leave this question also. Now next, this CH3Br plus nucleophile gives the following reaction. The decreasing order of the rate of the above reaction is the following one. Okay, so you have to decide that which one will be the giving the higher and which one will be the lowest rate. Okay, so this is the PHO minus, OH minus, ACO minus, CH3O minus. So you can do it by yourself by recognizing that which of the following is the better nucleophile. So we have the three options that are DCAB, DCBA, ABCD and BDCA. So you can do it by yourself. So this was all for today's class. So you can solve this question by yourself. Tomorrow we will be dealing with a new chapter. Okay, thank you. If you have any questions, you can ask.